Hi, welcome back to es346 Basic Thermodynamics. This is module 7.4, TDS relations. The sections in the textbook are 7.7 to 7.8. Here are the two learning outcomes for this module. At the end, you will understand the two forms of TDS relations for determining entropy change, and you'll be able to calculate the entropy change for processes involving incompressible materials. All right, so first I want to go ahead and derive what's known as the first TDS relation. And what TDS relations you'll see do allow you to determine the change in entropy. So recall from the definition of entropy, ds is equal to the integral of del Q over T. Actually, we say delta S. And so if I could go ahead and monitor what the temperature is as I add a bunch of Q's into a system or remove a bunch of Q's and do that integral, I can determine the change in entropy. So for example, if I had this piston cylinder device and I was to go ahead and add some heat Q to it and maybe it was going to expand so it would do some boundary work. If this was, for example, an ideal gas, the temperature would increase as I added the heat. And so each time I would need to monitor the temperature for each amount of Q that I put in, and that becomes sort of laborious. And so I'd like to have some other way to do it that's a little bit simpler, particularly since entropy is a property. I should be able to do it by measuring other properties, and that's what we're going to demonstrate here. So let's go ahead and look at our closed system energy balance for this piston cylinder that I drew up. Delta E is E in minus E out, and so that change in energy, we'll consider just the change in internal energy, delta U, and the energy that goes in is Q, and the energy that goes out is going to be the boundary work. Now, I'm going to go ahead and substitute this Q with this relationship that I have up here. So let's go ahead and just write this in differential form first. So I'm going to write du is equal to del Q minus del WB. So I'm just considering little incremental amounts. And so in place of del Q, I'm going to go ahead and put in T ds. So that's going to be equal to T ds. And now I've replaced it with a differential. And the boundary work, this is PdV work, that's going to be minus PdV. And that is all equal to du. So I'm going to go ahead and rearrange this. I'm going to move the PdV term over here and divide through by T. And so I end up with ds is equal to du over T plus P over T dV. And write that in extensive form this way. Well, this is actually a pretty powerful relationship, and this is what I'm calling the first TDS relationship, and you see where the TDS comes from right there. But what this does is it lets me calculate what changes in entropy are by things that are really easy to measure. Pressure is fairly easy to measure. I just need a pressure transducer. Temperature is easy to measure with a thermocouple. And du, we can actually determine that. We've been doing that for the first half of the semester with the first law of thermodynamics. We can integrate over changes in volume. So entropy, which is a fairly eccentric property, and there's no entropy meters, but there are definitely meters that I can go ahead and use to measure these other properties. So this equality is pretty powerful. I'm going to go ahead and derive a second relationship that's going to spur off the very first one. So right here I have written up here is the first TDS relationship that we just derived. And I'm going to just go ahead and make a couple substitutions. So first, recall that the enthalpy is defined as U plus PV. Right? That's just by definition. And so if I was to take a differential amount of that, so I'm just going to do a differential here. This is just calculus at this point. dH is going to be equal to du plus P dV plus V dP. So just calculus. No thermodynamics there. But what I'm going to do now is substitute this du plus PdV in up there. So I'm going to move my VdP term over to the other hand side and put it in. So now I have T ds is equal to dH minus V dP. And so what I've derived here is my second TDS relationship. I could write it this way. ds is equal to dH over T minus V over T dP. And I have a second relationship for determining what the change in entropy is, again with measurable properties: temperature, volume, pressure, and enthalpy. And both of these accomplish the same thing. I like to think of them as a set of wrenches where one may be metric and one is English. They both turn bolts, but some just tend to work a little bit better than the others. And we'll end up using both relations in the next few modules. So let's look at what happens to this TdS relationship if I have an incompressible material. So here's my incompressible material. I've got it drawn up here as a bunch of individual molecules. And if I was to go ahead and add some heat to it, say some Q, right, what I end up doing is changing its entropy. We know that if we add heat, we change the entropy of things. But if this is incompressible, the volume wouldn't change. So if I look up here, this dV term is going to be 0. So I can go ahead and just cancel that right out. And I end up with now simply TdS is equal to du. And we also know that for incompressible materials, du is equal to Cv dt. So if I divide through by temperature, I have that ds is equal to Cv over T dt. And if I now, this is all in terms of temperature, particularly if I assume a constant heat capacity, I can determine what my change in entropy is. And it's going to be the integral of Cv over T dt. And if Cv is constant, this is simply Cv ln of T2 over T1. So that tells me what my change in entropy is. All I need to know is the beginning and end state temperature. So let's go ahead and do an example like this. What I have here is a brick wall. It's 5 centimeters thick. It's initially at 25 degrees Celsius, and the sun is shining on it. It's shining on it at a rate of 350 watts per square meter. And I want to know, after 1 hour, what's the change in entropy of the wall, right? So we know if we just saw from that previous delta S, and I'll write this in extensive form, delta S is going to be M Cp ln of T2 over T1. Recall, Cp and Cv are essentially the same for incompressible materials. So there's just essentially one heat capacity value that I have. So if I wanted to go and determine it for this problem, the mass of it, if I just go look at, for example, 1 square meter, since that's the amount of energy coming in, this would be the density times the volume Cp ln of T2 over T1. Right? So I'm going to go ahead and put some values in here. And so I can get values for brick from table A3. And I'm going to go ahead and plug those values in here. And so the density of brick is about 2,300. The volume is going to be 5 centimeters, or 0.05 meters by 1 meter. So right there is my volume term. And then Cp of brick is about 0.96. These are all in SI units. And then I've got the natural log of T2 over, and T1 is 25. Now, a couple things here. This always has to be an absolute, so I'm going to put 273 on there in the denominator. But I need to know what the final temperature is. And so what is the final temperature of this brick wall going to be after an hour with 350 watts per square meter? Well, what I need to do is I need to do an energy balance, which says that the change in energy, delta E, is E in minus E out. In this case, I'm just going to have M U2 minus U1 is equal to Q, right? Or essentially Q dot times the time. So that's going to go ahead and tell me what the change in internal energy is. For an incompressible material, that's MCP T2 minus T1. So that's where I'm going to go ahead and get T1 from. So let's go ahead and put our numbers in there to go ahead and calculate what that is. And so again, for the mass, I'm going to do my density volume. So I have 2,300 for the density. My volume is 0.05 and 1. So meter, square meters there, and meter, so 0.05. Cp value is 0.96. And now I've got T2 minus the initial temperature. I'll do this in Kelvin, so this is 298 Kelvin. And that right there is equal to Q dot times time. So 0.35 kilowatts. It's 350 watts. And then this is going to happen for an hour, or 3,600 seconds. So now I can go ahead and solve this equation for T2. Go ahead and give ourselves a new piece of paper here. And if I solve that first law energy balance, I find T2 is equal to 309 Kelvin. So now I can plug this in, my result from the first law, into the second law equation. So delta S is equal to, I'll rewrite that, 2,300 and 0.05, 1. So my density and my volume term, my Cp term, 0.96. And now the natural log of T2 is 309, and T1 is 298 in Kelvin. And that's going to tell me what my change in entropy is, and change in entropy is about 4.00, and the units of that are going to be kilojoules per Kelvin. So that's how much the entropy is. The entropy increased, energy went into it, and it became somewhat more disordered. Let's go ahead and do another example here, a little bit more complicated, but again working with incompressible materials. And I've got a 2-pound brick. It's initially at 400 degrees Fahrenheit. And what I'm going to do is I'm going to place it into a gallon of water that's initially at 60 degrees. So let's draw down our little bucket of water here. It's got 1 gallon. It's initially at 60 degrees. And I'm going to let them thermally equilibrate. And now I know what is the total change in entropy of the system. And so what's happening is the water is going to heat up, so its entropy is going to increase. The brick is going to cool down. Its entropy is going to decrease. And I want to know what's the total change in entropy. So, well, first of all, we know we have to find out what our final temperature is. We need to find out what is T2. And T2 of the water is going to be the same as T2 of the brick. So I need to do my energy balance. And so I can write it this way. The change in energy of the water is going to be the change in energy of the brick. All right? And so they're both incompressible materials. So the mass of the water, C of the water, T2 minus 60 degrees, and there's a change in energy of the water, has got to be the same as the energy from the brick. It's going to be the mass of the brick, C of the brick, and that will be 400 minus T2. So now I need to go ahead and solve this equation to find out what is T2. I'm given a volume of water, not a mass of water, so let's go ahead and determine what that mass is. The mass of the water is going to be the density times the volume. So I've got 1 gallon, and then I need to go ahead and have 61 as my density. That's pound mass per cubic feet. I can get that off of table A2. And then I need to go ahead and do a conversion factor here of 35.3 cubic feet is 264.2 gallons. That's out of the back cover of the book. So now my gallons go ahead and cancel. My feet cancel. I'm going to end up with something in terms of pound mass. And so it turns out my water has a mass of about 8.15 pound mass. So now I can go ahead and put that in for the mass of the water here. So let's go ahead and write that energy balance with all of our numbers. 8.15 mass of the water. C of the water is 1 BTU per degree Fahrenheit, pound mass. And that is T2 minus 60. And then the mass of the brick, problem gives that at 2 pounds. C of the brick in English units is about 1.89. That's out of table A3. And now I've got 400 minus T2. And I'm going to go ahead and solve this equation here for T2. And I find out that T2 is equal to 75.1 degrees Fahrenheit. So I realized the water went up about 15 degrees and the brick went down several hundred degrees. Right, so now I have T2. Now I can go ahead and calculate the second law to determine what my change in entropy is, total change in entropy. So, well, the total change in entropy is going to be the change in entropy of the water plus the change in entropy of the brick. Remember, if the brick's entropy is going down, putting it into the water, that entropy is going up. And I want to know what is the total change in entropy. So for each one of those, that's going to end up being equal to MC ln of T2 minus T1, all of that for the water, plus MC ln of T2 over T1, and all of that for the brick. So we're going to put our numbers in there. For water, we had 8.15 was the mass. C of water was 1. Natural log of T2, that is 75 degrees. And recall, these need to be in absolute, so I'm going to add 460 over 60 plus 460 for T1. So there's the change in entropy of the water. And I'm going to add that to the brick. 2 pounds, CP of brick is 0.189. And then the natural log of T2 again is 75 plus 460. And this started off at 400. At 460 to get it in absolute as well. And now if I do that arithmetic, this comes out to be 0.05235. And the units on that are BTUs per degree. Right? So a couple of things I want to point out here. First of all is that if I look at the water term, this first term right over here, this was a positive contribution. This is a positive value, so this is an increase in entropy. The second term was a negative, the brick, so it had a decrease in entropy, yet the net change was positive. Right? And then we'll see that the total change in entropy for any process that spontaneously happens is going to be positive. And in fact, if the total entropy went down, it actually can't occur in the universe. So one of the things you might wonder is, I've just been using these entropy changes for water using Cp ln of T2 over T1. Right? I said delta S is equal to Cp ln of T2 over T1. I did that for water, but we also recall when we have our water tables, this is table A4 I'm showing, over here on the far right are entropy values. And it turns out that actually both of these equations for incompressible material would give me the same value. So for example, let's just look at water going from 100 to 105 degrees Celsius. So I was to put that into this equation here, Cp of water in SI units is about 4.18. And this would be the natural log, and again this has to be an absolute, so that would be 378 over 373. And that value there is about 0.0556, and it's going to be kilojoules per kilogram Kelvin. So that's what the change in entropy for water is going up that 5 degrees. Well, if I was to look at the difference between these two values right here, this is the saturated liquid water. I got 1.3072, 1.3634. I'd find out that that change in entropy is the exact same. So these tables for liquids are going to give me the same value that these equations give. But this is only good for incompressible, so it doesn't do any, we don't want to use those if we're using vapors or anything that's being phased.